All right, next we'll have fast and extensible hybrid embeddings with micros by Sean Bocirnea.
Type checker when that sounds a bit more loud. When we're doing type checking, so if we don't care about performance, then we're not going to be able to type check anything really. And because this is a research language, we care about it being extensible so that we can play around with changes to our typing judgments and stuff like that. And really, this talk is about these three properties. How do we get a framework that is interoperable, extensible, and has performant compilation? Now, this isn't just a toy problem. There are people in the real world who want languages that are both extensible and quick to compile. One such example might be something like Agda. Plenty of new type theories are tried out in Agda. Some are like cubical, rewriting. And another language that has a large community of extensions is WASM. So most recently, the garbage collection and multi-memory are in the pipeline. But more importantly, for both of these examples, performance really matters. So Agda's got a complex dependent type system, so it's got the same problem that we do. And WASM is just-in-time compiled, oftentimes over the web while people are waiting. So it's important that it compiles quickly. Cool. So back to our three goals. Each of these requirements needs maybe a bit more clarification. So because we want interoperability with Racket, what this really means is that we need a shallow embedding. So what shallow embeddings do is that they let us mix host and object language syntax, which for our purposes we need in order to understand the implications of our gradual type system. And what this looks like really is that, for example, if both Racket and FOWL have a concept of vectors, we can call vector operations from one language on vector representations from the other. On the topic of extensibility, I want to clarify that there's a distinction here between extensions and modifications. So when I mean extension in this talk, what I really mean is separate compilation. So we have some base language, and extending that language means that you don't necessarily have to destroy the properties of the base language. By contrast, a modification is a change that's made to the base language which overwrites the semantics of the original version. So with something like this, I would argue that these are more modified languages, because even if you can turn off features with compiler flags, the implementation of these languages still needs to be carefully managed by the language implementer, and at some point in these language implementations, the coexistence of these possible sets of features still needs to be carefully handled. And lastly, we're only worrying about compile time performance here because it's far more dependent on the compiler framework, and it's far more important for complicated type systems. And runtime performance of a language is a lot more dependent generally on particular implementation or particular optimizations that are performed. So, all right. Here's where we're at. Right now, we've got some programming patterns that we can use to implement all this. But in the future, what we really want to do is package these patterns into some abstractions that make it a lot more straightforward for people who want to implement their own languages to use our work. And yeah, eventually, hopefully, this might look like something like a meta DSL. Okay, now we can update our roadmap. And let's talk about existing approaches. But first, pop quiz. So when we're compiling, how would we like to represent our programs? Well, I've been told a lot that programs are data, but I guess there might also be syntax because they are just a bunch of symbols, but we traverse them like data. But, well, maybe if we understand better what we mean by each of those, we'll be able to pick. So let's dive into that a little bit. There are really two kinds of syntax that we usually think about. The first is concrete syntax, just program text, whatever your favorite encoding is. But especially in Scheme and Racket, when we talk about syntax, we also mean abstract syntax. So stuff like S expressions, which are just a tree of arbitrary symbols. It's a very permissive representation, and very importantly for this talk, a valid S expression is not necessarily a program in any particular language. I want to contrast that with data, which I'll be using to mean really well-specified IR, which only admits terms of a particular language. So instead of arbitrary trees, we have something like tagged terms with very well-defined children. And if I use syntax and data in the rest of the talk, I mean these two categories. Cool. Well, now that we've made that distinction, I think it's still important to take a look at what some related work does before we decide. Three related works drove our design decisions here. Turnstile Plus is a Racket library that allows you to encode type systems as macros. LMS is a Scala library which gives you staged metaprogramming. It lets you define languages in terms of Scala classes. And syntax spec is another related work that is also built on top of Racket. It gives you the ability to extend a language using hydronic macros. And interestingly enough, all of these three have a different way of representing programs. So Turnstile Plus keeps everything in what we'd think of as syntax. LMS, the entire pipeline is this structured IR, which has which you need to define for each language. So that qualifies in our idea of data. And syntax spec does a bit of both. The macro system lives in syntax land, and then eventually you do actually have to convert everything to some static IR. And in each of these tools, this is where you'd perform program transformations like optimizations or type checking. And in the case of Turnstile Plus and LMS, these transformations are extensible. So it's possible to change the type theory of the language without clobbering a base language. But in syntax spec, while it is possible to extend the syntax of a language using these hydronic macros, the transformations on data, like type checking and whatever else one might want to do, are not extensible. So each of these, in different ways, fails to hit all of those three metrics that we're interested in. But we start to look at this graph here, and we start to notice that, well, maybe we can kind of take the syntax part of Turnstile Plus, which is extensible, and then maybe, go and steal a little bit of the data part of LMS, and get something that will work for us, that will be both fast, extensible, and have good interoperability. And you can also think about this as making the data part of syntax spec extensible, either or. All right, so back to our quiz. Well, I guess both. We should pick both. In other words, what we really want is a hybrid embedding. So we have something that looks to Racket like it's Racket syntax, but in the back end, we have a AST that we've constructed that we can churn on, much like LMS. Okay. Nice. So how do we do it? Well, first we need to talk about macros and micros. And to talk about macros, we'll start by taking a look at how Racket represents syntax. You're all familiar with S expressions. Basically, Racket syntax objects, which its macro system operates on, are just S expressions with some scope information. And both Racket and us use that to resolve binding. So, quick refresher on macros. Say we have a list macro. We spit out this sequence of cons. Really, the important thing here is that macros are syntax-to-syntax transformers. And when we look at how something like maybe Turnstile Plus uses macros, really what happens is that you start with some program text. Racket's reader does the job of turning that into syntax objects for us. And then Turnstile Plus just loops in this macro expander in order to resolve all of its typing judgments and finally, at the end, spit out core Racket, which is understood by Racket's compiler, and then executes. Well, this is great. Both of these are nice and extensible. Racket's reader and macros are very easy to extend. You can use Racket's module system to do this and separate your languages, all well and good. But all of the work is here. And unfortunately, in the case of Turnstile Plus, because it's modeling type checking operations, the expansion of order of macros conflicts with the order of type checking. So to make matters worse, what happens is that in order to encode these typing judgments, more macros are emitted during type checking, which are then expanded. And anyways, this blows up. And to make it even worse, Racket syntax objects in particular are represented using linked lists. So they have quite poor access properties, and things can start to get quite slow. All right, so if macros are the problem, then I guess let's get rid of them. But we've kind of got a hole here. Well, you know it already. We're putting micros. But, well, what are they? Okay, let's take a look at our list again and say this isn't a macro, say that it's micro instead. We might expand that into something more like this. So we've got a set of structures now, and notice that there's no hashtag here. So this is not syntax, this is data. And indeed, that's what micros are. They're expanders from syntax to data, and this is not a new idea. Sriram's PhD thesis covered this. But we use a different representation for our data IR. We don't actually use Racket syntax objects. What we use is Racket structs. So these are just named records, really. In this case, the name of this record is construct. Maybe it has two fields, car and cutter. And in addition to that, Racket also gives you the ability to attach generic methods to these structures. In this case, we have something that we'll call elaborate, and then we can specify the implementation of elaborate for cons specifically, just attached to the definition of cons. So we use these generics in our circumstance to encode our typing judgments and encode any other transformations that we'd like to perform on our data AST. So in the case of elaborate, this is a particularly important one that every language that uses our framework will need to implement, because this is the very last transformation that we perform to spit back out Racket syntax that we can actually run. So the elaborate generic is what you use to encode your runtime semantics, but you can have plenty of generics for whatever you'd like to do, including a separate one for type checking, or if you have bidirectional typing, maybe you'll have two. Anyways. These are features that we'll use to build a language. So first of all, turns out that you need a bit more than just micros to fill this gap. So what we really need is 3 separate steps. You may be looking at this and thinking, wait a second, you got rid of macros, but you're adding them back in. And that's because it's still useful to have some macro functionality for stuff like syntactic sugar. Note that we never loop through the macros. We do one macro expansion pass for whatever syntactic sugar might be useful, but we don't use macros to encode typing judgments or program transformations. Neither do we use micros to do that. Micros simply take a syntax object and then spit out our struct AST. And then, using the generics that we talked about, we loop over that struct AST, perform program transformations, perform type checking, and then at the end, via that specific elaborate generic, we spit out our syntax objects that are in Racket core that are the actual runtime behavior of our programs. Cool, so all the work is here. And it happens on a mutable data structure that we can update in place. Our syntax is only expanded once, and to top it off, Racket structures have O of 1 access on any fields. So things are looking pretty good. And this isn't just theoretical. We also built a dependently typed language using this framework, and we are about 100 times faster than Turnstile Plus on a suite of dependently typed benchmarks. That thing right at the bottom there is the fastest dependently typed type checker that we know of. We're not quite that fast. We're still about 3 orders of magnitude slower than that. But we are only 1 order of magnitude slower than stuff like Lean or Agda, which are modern in production dependently typed languages. All right, so we made it fast, but we still need to make each of these extensible. Well, Racket does both of the first ones, and with some ad hoc programming patterns, we can do the second ones. And we did indeed manage to extend our language in some pretty cool ways, including modeling even the gradually typed part of it as an extension to a non-gradual dependently typed calculus. But that's not very nice. So we'd like to make each of these different parts of our language extensible more neatly. We'd like some nice abstractions that package up what we really needed to do there. So again, the reader and macros are extensible, but because our struct AST is not inherently permissive, extending micros and our struct transformations takes a bit more work. And really, we nailed down 3 abstractions that are needed to make this work. For micros, we need extensible micros. And for our AST transformations, we need some way to extend structs and some way to extend generics. And really, each of these maps to a different class of extensibility in our object language. So with extensible micros, you get extensible language syntax. And with extensible structs, you can extend individual transformations on particular language terms. And with extensible generics, you can add new classes of transformations. Cool. So let's take a look at the first of those abstractions. Just as a refresher, with macros, you expand till you run out of them. All well and good. But interestingly enough, to get a hybrid embedding with micros, we have another interesting problem, which is that we now need to recognize which syntax objects are actually part of our language and which aren't. So in this case, if we expand this list micro, okay, we need a structure that's representing the list term. But then, well, we only have the list micro here. 1, 2, and 3 are just Racket core. So I guess maybe we put Racket core syntax here, but wait a second, that's not an IRR. That's not wrapped. We have no way of attaching semantics to this. So really, sometimes we want to actually be able to recognize Racket core IR as well and turn those into our AST. And just a side note here, it's a bit more complicated. We sometimes want to keep the source syntax around, especially for binding. And if you want to see the backup slides, you can ask about it. But the 2 ideas are basically we need to recognize an AST extensibly, and we need to be able to shadow and add new macros so that we can add new language terms. All right, so extensible structs, a bit more straightforward. Say we have this lambda, and it expands into an AST. Cool. This is untyped, though, and we talked about types a lot, so maybe we want to add types. And to do that, we're going to need to add some annotations to our syntax. Okay, I believe I can do that with extensible micros, but that means that we'll need to annotate some of our variables so that we can perform type checking, right? So, okay, we put nat in there, but that means we need new fields. So if we look at what the struct might look like, say it's just got 1 field symbol, then we'll need to add a new field type, and indeed we might even need to change the implementation of some of the generics so that now we use this type information. Perhaps we want to preserve it across modules, whatever else. In particular, we need to change generic implementations, and we need to change the fields that particular structs have. Cool. So we've added types to the structs now, but maybe we want to actually use them. So we'll need some way to add new generics. We need to add a check generic in this case so that we can type check our language forms. And in addition, we might even need to change the signatures of existing generics. So say maybe elaborate is now type directed. This is a bit of a contrived example, but in general, we did need the ability to change existing generic features, especially for the gradual typing extension. But these are the 2 requirements that we settled on for an extensible generics abstraction. All right, so we've kind of figured out what we want. Let's try to implement it. Turns out we can do micros. That's not too bad. But the other 2 are a bit more difficult. We've got a pretty good idea of how to implement extensible structs. In particular, the thing that is really tricky for extensible structs is that Racket has this concept of structure properties, and these are a bit harder to proxy. But extensible generics kind of uses these a lot, and because we haven't figured them out for extensible structs, extensible generics have us quite stumped. So just to wrap things up, if you want hybrid embedded languages that are extensible and compile quickly, You can use micros to elaborate a shallow embedding to a structure IR. You can then use generics to type check, transform, and emit host language code. And then, after we figure it out, you can use our abstractions to make it extensible. For now, we have some programming patterns that let you do that, but really what we'd like out of this talk is to be able to chat and see what ideas you all might have for how we might implement these abstractions. All right. If you found this interesting, a lot of my colleagues have given talks on related topics. You can catch the recordings if they happened in the past. Thank you very much for coming.
We have a question in the back here.
Very nice talk. It's very good to see someone try to figure out forms of extensibility that go beyond macros. Macros are very powerful for extension, but there are other ways to extend that macros can't always reach. It's good to see that. Does the work you're doing have to deal with hygiene?
We don't tackle hygiene specifically. Indeed, syntax spec does, which is one big difference. They're concerned specifically with providing functionality for having hygienic macros in between languages so that you can't use language forms that are not in your language. So, for example, this might be useful for our gradual embedding. But right now, with this work, we were not concerned with hygiene in between languages. We have the hygiene guarantees of Racket's macro system for our surface macros, just our sugar macros, but we were specifically worried about being able to model our extensions and did not concern ourselves with a micro hygiene system.
So do you mean that you're ignoring hygiene currently, or just that it doesn't interact with the layer at which you're operating?
We inherit hygiene in a lexical sense from Racket's macro system, which we use to implement our micros. We do not have a concept of hygiene akin to something like syntax spec in between different languages.
Okay. Second question, if I may. You mentioned you're working in a dependently typed language. Yep. The natural thing there is proofs. And so I'm wondering if, similar to my question in the last talk, if you can have access to some sort of element of your context. So in a proof, if you want to write a macro that represents a tactic, it would be nice if that macro could know what type is being expected by the surrounding context.
Well, there are two parts to this question. First of all, when we're talking about a module that is specifically in maybe like just a foul module, because it's a hybrid embedding, we'll have a deep representation of the AST, and then while I'm not familiar with the specific requirements of tactics, I would imagine that because we have a full program available to us at that point, we'd be able to perform whatever context-dependent analyses are required. Intermodule, things get a bit more interesting. We need to find some way of compiling to a Racket core language that allows us to preserve some of this typing information so that it can be read back by whatever other module needs to be compiled on top of this base module. And that is something that we've developed our system with in mind, but since we haven't written something like a tactic system, I can't guarantee that is expressible. But within a module, I feel reasonably certain that would be possible.
Okay, thank you.
We have time for a quick question.
Afterwards, yep.
Yeah, I was curious, the problems you're having with, or maybe not problems, but future work with structs, is that dependent on your choice of representation of the IR as structs? Like, if you rewrote it to be represented as classes, would that change anything or change nothing?
For example, LMS has a class implementation. I believe Ziggurat also has something like classes. It has objects in the background. That eases some of the concerns with regards to implementing the abstractions. But internally, we ran some performance tests and noticed that for Racket particularly, we had quite a significant overhead when using objects, specifically memory footprint and also access time. So that's what led us a bit towards structs.
Yeah, we can talk later. I just want to know if it would fix extensibility issues like the extensible generics.
It does help at the cost of performance.
Gotcha, thanks.
All right, let's thank Sean again.